Welcome back to a new lesson. Today is a fine day for science because we will learn the mathematical concepts behind a neural network and we will implement one in Python by only using the library NumPy. If you didn't watch the previous lesson, I recommend you to stop this video, watch the first one. You can find it in the description and then come back to this one because there we talked about the concepts behind the neural network. And now we will get into the mathematical operations. Let's see. We have here a diagram of a neural network. It's the same one as in the previous video. Let's recap a bit what it contains. We have the input layer, which has three elements. We have the hidden layer and the output layer. What we are trying to do in a neural network is finding the right values for the weights between the neurons so the output can have the best accuracy. So you will give the input, for example 1 1 1, and based on some mathematical computations you will get an output. First you will initialize the weights with some random values and then you will start optimizing them until your error is as close as possible to zero. What we will try to do in this lesson is classify some animals based on three characteristics as mammals or birds. Let's see. We have a pigeon. A pigeon will be represented as 0, 0, 1. In the input layer, each of the elements represents a characteristic. For example, the first element can be seen as has fur, and you can continue like this for the other two. Now, for these input elements, we will provide some outputs. For pigeon, represented as 0, 0, 1, which is a bird, and will output the 0 number. 0 will be decoded as bird, and 1 as a mammal. So dog, represented as 1, 1, 1, will be a mammal. Cat, 1, 0, 1, will be represented as mammal. Parrot, encoded as 0, 1, 1, which is a bird and will output a 0. To be able to train your neural network, you usually have to do some steps. You have first to do some training where you provide some data that your neural network can train on. Next, you have the validation part where you provide different data to your neural network so you can see that your network didn't memorize the training data. We want our neural network to memorize the general pattern. In our case, we won't have the validation part because we don't have that many elements, but if you want, you can take an array of 5, for example, and you can split some data for the validation part. And next, the testing part, where you provide, for example, real-world data and see how good your neural network will perform. Let's now get into the mathematical representation. We have here the diagram, and we now have to start to represent our layers and our weights. We will represent them as matrices, so the computations will be easier to understand. Let's get into the mathematical operations behind training and predicting something with a neural network. First, you have to know that we have to transpose this diagram into matrices operations. For example, we have the input layer and the weights. These should be written as matrices, and they will look like this: x11, x12, x13. The input array will be transformed into a matrix of 1 line and 3 columns, and will be multiplied by the matrix of weights between the input layer and the hidden layer. On the first line, we can see the link between the first neuron in the input layer and the hidden layer, these ones. On the second line, we will see the weights between the second neuron from input layer and the hidden layer. And on the third line, we will see the link between the third neuron and the hidden layer. By multiplying these matrices and then applying an activation function, we obtain the hidden layer. Let's stop a bit at the activation function. This is a complex topic, but just for you to know, we use an activation function. Make sure that our neural network introduces non-linearity. To be short, the activation function tells the neural network which neurons to fire and in which proportion. Think of it as a light switch. So we will have a nonlinear relationship between the input and the hidden layer, meaning that a minor change in the input can cause a big change in the output. So the change in the input is not proportional with the change in the output. That's what nonlinearity stands for. Next we have the matrix of neurons from the hidden layer, and we have to compute the output. So we take the hidden layer values and we multiply them with the matrix formed with the weights between the hidden layer and the output. We apply the sigmoid function and we have the predicted output. It will be a function that is between 0 and 1, and if it's between 0 and 0.5 we will round the result to 0, and if it's between 0.5 and 1 we will round the result to 1. Now that we talked about the mathematical implementation, I would like us to start coding the neural network. I will open PyCharm. First, make sure you import NumPy exactly like this, and then write the main entry point. What we have to do? We have to provide the input. For us, the input will be the arrays that we saw in the article. These ones. 001, 111, 101, and 011. So, np.array, and now we have to provide the matrix. We will do something like this. Each of these pairs will be a line. So we will have 4, and let's start actually completing them. 0, 0, 1, 1, 1, 1, 1, 0, 1, 0, 1, 1. Now we have to provide the outputs array. Outputs equals np.array, and we'll have to provide a matrix with 4 lines and 1 column. For the first one we will have 0 as an output, 1 for the second one, 1 for the third one, and 0 for the fourth one. Next we have to initialize our weights. How we will do that? We will do it by using the NumPy generator. First let's input a seed. We would like to use a seed of 1, so the generated numbers will be close to each other. Next let's generate the weights. First we will generate the weights input layer, hidden layer. We will do that by using NumPy np.random because we want to initialize a matrix with 3 lines and 4 columns, and now a minus 1 here. Weights hidden layer output layer will be 2 multiplied by np.random of 4 lines and 1 column minus 1. Now we have the weights generated. To be able to train a neural network, you have to run the same operations for a given input and output several times, and for each iteration you will have to optimize the weights so that the output can be as accurate as possible. Let's do that. For epoch in range of 10,000, and now we want to run this iteration for each input that we have. So for I in range of inputs dot shape of 0, this will take the number of lines. We need the input current element as np dot array, and we will take inputs of I because we want it to be a matrix of 1 line and 3 columns. Output current element equals np.array. Next we will use the square brackets because we want it to be a matrix, and inside we will take outputs of I. Now we have to compute the hidden layer and the output. How we will do that? We will have to do what we have seen in the operations example. We will have first to multiply the input by the weights, then apply the sigmoid function and obtain the hidden layer. After that, we will use the hidden layer to multiply it with the array of weights between the hidden layer and the output layer, and we will apply the sigmoid function, then get the predicted output. Let's do it. Hidden layer equals np dot. This will multiply the matrices that we provide to it. So first we will provide the input current element, then we will provide the weights between input layer and hidden layer. But we will also need the sigmoid function. We will have to define it. Let's do it here. Def sigmoid of x, and it will return exactly what the sigmoid function does. Let's write it down. 1 divided by 1 plus np.exp of minus x. Let's have a space here. So now let's use it. Sigmoid applied to the result of the multiplication. We have now the hidden layer. We will have to do the same for the output layer. So output layer equals sigmoid of np.dot, and we will use the hidden layer and the weights between the hidden layer and the output layer. Weights, hidden layer, output layer. And now we have the forward passing ready. If you want to predict something, you would just stop at this operation and not run it for a number of times, just for a single input. Let's run it with the debugger and actually see how our elements are looking. Let's see how the weights between the input layer and the hidden layer are looking like. We can see that it's a matrix with 3 lines and 4 columns. Let's take a look at the weights between the hidden layer and output layer. Evaluate view as an array. We can see that we have a matrix of 4 lines and 1 column. Let's see how the forward passing is going. We can see that the input current element will get the first element from the provided inputs, and the output current element will get the first element from the provided outputs. Now, this will multiply the input current element with the weights between the input layer and the hidden layer. If you want to verify this operation, you can do it. We will get an array with 1 line and 4 columns. Now we just apply the sigmoid function to induce nonlinearity, and the result will look something like this. Keep in mind that if you run the program, because the weights were randomly generated, you won't have the same values as I have. So don't panic if you see this. Close, and let's continue. Now we have the output, the predicted one. We have to start to see the difference between the predicted output and the actual output, so we can update our weights to predict better. The first error will be calculated as the predicted output minus the actual output. Then we will have to calculate a delta, the values that we will use to adjust the weights, and will be computed as the error multiplied. Keep in mind, this is not matrices multiplication, it's just a scalar multiplication, multiplied by the sigmoid function derivative of the output. When we find the adjustment for the layer 2, we have to go back and find the adjustment for the first layer. So we start calculating the layer 1 error, and we will do it by multiplying the delta obtained for the hidden layer with the weights between hidden layer and the output layer. Keep in mind that we use the transposition of some matrices, so the computation can be possible. And the last part of the backpropagation is calculating the delta for the hidden layer. We will use the error. We will multiply it with the derivative applied to the neuron values of the hidden layer. Maybe this sounds confusing a bit right now, but we will do it in code, and we will use also the debugger to visualize it. Let's get back to the code. Stop the program. First, we have to compute the output layer error. We will do it by subtracting the output layer from the output current element. minus output layer. Now we have the output error and we need to calculate the delta. Output delta equals output layer error multiplied with sigmoid derivative, which we will have to define, of the output layer. Let's define the sigmoid derivative. Def sigmoid derivative of x and return x multiplied by 1 minus x. We are writing the derivative like this because it's in relation with the sigmoid function. Let's see exactly what I'm talking about. So this is the sigmoid function and can be written like this in relationship with the sigmoid. Because we have the result of the sigmoid function, and that being the output, we just need this formula. Now we have the output delta, and we need to continue the calculation of the error and the delta for the weights between the input layer and the hidden layer. Hidden layer error equals np dot output layer delta and the weights hidden layer output layer transposed. Now hidden layer delta equals hidden layer error multiplied with the sigmoid derivative of the hidden layer. And now we found the adjustments for our weights. The last part of training a neural network is the weights update. First, we will have to update the weights between the hidden layer and output layer. Then we will have to update the weights between the input layer and the hidden layer. We will do that by adding the multiplication between the matrix that represents the hidden layer transposed and the delta for the output layer. The weights between the input layer and the hidden layer will be updated by using the matrix that represents the input layer transposed multiplied with the delta of the hidden layer. Let's do that. Weights input layer hidden layer plus equals np dot weights hidden layer output layer plus equals, and now np dot hidden layer transposed multiplied with the output delta. Weights hidden layer output layer plus equals np dot input layer transposed multiplied by the hidden layer delta. Now let's test our neural network. How we will do that? We will just have to compute the output and compare it with the actual output. Layer 0 equals np.array of 0, 0, and 0. Hidden layer, let's call it layer 1, equals sigmoid of np dot and we multiply the layer 0 with our weights. Weights input layer hidden layer. Let's make it as an array here. And the output, predicted output, equals sigmoid of layer 1 multiplied by the weights between hidden layer and output layer. And now let's just print the output. Print predicted output. And we would like to see the errors at each iteration. So print iteration epoch, print error output, output layer error. This will have to be smaller and smaller as we go. Let's give it a try. First with the debugger to see that we have written everything as we should. We have the input current element, we calculate the hidden layer, now the output layer, we compute the output layer error, output delta, and now we start to compute the hidden layer error, hidden layer delta. We see the epoch and the error output. We update the weights. We actually have a small mistake here. The weights that we are updating at this step are not the ones between the hidden layer and the output layer, should be the weights between input layer and hidden layer. So let's rerun again and see if now it's okay. We compute the hidden layer, the output layer, the error, delta, the hidden layer error, the hidden layer delta, and let's see if we actually get through this. Now I want a breakpoint right at the end. Let's look into the console. You can see that the error is becoming smaller and smaller. Now we have the neural network trained. So now it should predict other values too. Let's take a look at our input. We provide 0, 0, 0. I would expect that the neural network to give us the output 0 because the characteristics are closer to the first one. So this should be a bird. Let's see how it goes. Oh, here we have a mistake. We forgot to multiply the matrix. np.dot between layer 1 and weights hidden layer output. Let's rerun the program again. And see what our neural network is predicting. So predicted output is 0.27, meaning that it's closer to a bird than to an animal. Now we know how to do a binary classification with a neural network. If you want, we can write a decode function. Def decode input, not input, result. And now let's write the body of the function. Categories is equal with birds, mammals. And return categories of result. And we can have here print the given output is classified as. And now we will just call the decode function decode of the predicted output, and we will have to round this to the nearest integer. And we will do that by using numpy dot round predicted output, put another parenthesis at the end, as type int, and the predicted output of 0, because otherwise we will input a matrix and it will give us an error. Let's run the program. And see how it goes. The output is classified as birds. Let's copy and paste this one more time and give as an input 1, 1, 0. 1, 1, 0. Let's see what our neural network says it is. It's a mammal because our input is close to this one. Only one characteristic is different. That's it for this video. I hope you enjoyed it and you watched it until the end. I know it's a lot of math, but if you want to continue your studies of data science, this base will help you a lot. If you like this video, please subscribe, comment what you would like to see next on this channel, and do not forget to like the video. If you want to see the written version, you can find it on my blog. Thank you.